So moving on to chapter 6, skipping over chapter 5 for now, but chapter 6 is our first kind of foray in this class into geometry and trig. And kind of starting in this first section with what should hopefully be a lot of prior knowledge for you guys with the usual new IB flavor. Just kind of getting acquainted with thinking about space, thinking about properties in space, objects in space, starting of course with our midpoint and distance formula. And this should be something that you should be all too familiar with. We know in 2 dimensions, right, where our prior knowledge is kind of stuck here in 2 dimensions. Right, we have an xy plane, and I can draw a line segment on that xy plane, and that line segment has points x1, y1, and x2, y2, right, with our subscripts. So we learned in geometry, right, that the midpoint formula is kind of given in 2 parts. The midpoint is a point, obviously, and the x-coordinate of the midpoint is halfway between my 2 x-coordinates. In other words, essentially it's the mean of the 2 points. And likewise with the y-coordinate, right? That's essentially the mean of the 2 coordinates. It's right in the middle of the coordinates. All right, so if I was to maybe like eyeball it, I'd say my midpoint's probably here somewhere. And the distance formula we know comes, you might remember, from the Pythagorean theorem, right? I would have been able to turn this segment into the hypotenuse of a right triangle, right? So I'll do this really quick. So this would be the length given by x2 minus x1. This would be the length given by y2 minus y1, and some distance d. Well, based on our Pythagorean theorem, we have square root of x2 minus x1 squared plus y2 minus y1 squared. And these are things that we already know. These are things that we've learned before in past classes. And now we're going to extend them out into 3 dimensions. And a lot of this extension is going to work very much the same as it had in 2 dimensions, just with one extra piece, right? You're used to having an x and y axis, but now in 3 dimensions we have an x, y, and z axis. So here are my 3 axes, and instead of doing x and y, we want to make sure we really think about up and down as being physically 3 dimensions up and down, right? So we'll call x is still where it's normally located, y, and then z. And I can still put a line segment in 3 dimensions, right? I can maybe draw a point out here somewhere, and I can draw a point out here somewhere. Maybe I'll actually move this maybe over here-ish. It's kind of tricky to see when you're trying to draw it in 2 dimensions, but these points have some coordinates, x1, y1, z1, and x2, y2, z2. Okay, so this line segment actually cuts through 3 dimensions now, even though you might not be able to see it that well here. Well, our midpoint, if we think about kind of logically from our 2-dimensional midpoint, I still need to go halfway between all of the coordinates, right? So I'll have x1 plus x2 over 2, y1 plus y2 over 2, and now this new piece, this z1 plus z2 over 2. Right, so this is the new piece in our extension. Likewise with our distance formula, I'm not going to try to draw it out this time, but you can kind of imagine that our distance formula likewise is just going to get lengthened by 1 term. So I still have my x2 minus x1 squared plus y2 minus y1 squared. And then my new piece, z2 minus z1 squared. So here are kind of my new pieces, my new versions, so to speak, of my midpoint and distance formula when we put these in 3 dimensions. So if we want to look at an example of this, I want to find the midpoint and distance of this line segment AB when A is at the point 125 and B is at the point 337. I'm not going to try to draw it out. Let's just jump right into the problem. Find the midpoint. All right, so my midpoint is given by, we usually call it M. And just for practice, let me copy down what the formula looks like. All right, well, fairly simple, right? x1 plus x2, 1 plus 3 is 4. We'll simplify it later. 2 plus 3 is 5. 5 plus 7 is 12. Dividing all those by 2, right, I get 2. 5 halves or 2 1/2, take your pick, and 6. There's the midpoint, easy enough. All right, well, the distance formula, again, let me just copy this down first. So, doing some work here, x2 minus x1. So as it doesn't matter which one you call 2 and 1 as long as you're consistent. But just for the sake of trying to keep things positive as much as I can, we'll stick with b as x, y, z, 2, and a as all the 1s, right? So 3 minus 1 is 2. 3 minus 2 is 1. 7 minus 5 is 2. So 2 squared is 4, plus 1 is 5, plus 4 is 9. Square root of 9 is 3. So we're still applying our midpoint and distance formula, no different than we're already used to. The other thing that should hopefully be familiar from geometry is starting to talk about the trigonometric functions. So IB, our book, talks about introducing the trigonometric ratios. But I've always learned it as calling it right triangle trigonometry, because right now, appropriately, we're dealing with just a right triangle, like I have right here, triangle ABC. And we're going to talk about one specific angle, that's this angle right here, and we're going to call it theta. That's the Greek letter theta. And we know that there are 6 trigonometric ratios, but we're going to just focus on 3 right now. There are 3 that are the most important. And it all depends on the combinations of sides that I want to consider, right? We're talking about ratios in some sense. Well, if I talk about relative to theta, so relative to my angle, right, there's an opposite side. So BC in this case is the side opposite theta. AB is the adjacent side. And AC is the hypotenuse. And it's worth remembering that the hypotenuse is always the non-perpendicular side. And the opposite and adjacent sides are always the 2 legs, the 2 perpendicular segments that come together to help form the triangle. Right, so we have opposite, adjacent, and hypotenuse. Opposite, adjacent, and hypotenuse. And as I said, you might have remembered from geometry, but there are really 3 key trigonometric ratios that we're going to deal with. There are 3 others, but they're based on these 3. Everything we do is based on these 3. So they are sine, which we abbreviate sin, theta, and that's going to be the opposite side over the hypotenuse. Based on our triangle here, that's the segments BC and AC. So sine of some angle is the ratio of the opposite and hypotenuse sides. We have cosine, cos theta, and that's the ratio of the adjacent and hypotenuse. So on our triangle here, that's AB to AC. And you don't really have to worry about these last bits. I'm just trying to put it in context of the figure that I drew. I'll box off the most important piece in a minute. The last bit that's important is tangent, right? And we abbreviate this tan theta, and that's the opposite to the adjacent. So on our triangle here, that's BC and AB. Really what you need to know, kind of classically, traditionally, we focus on these. Sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. You might remember the mnemonic SOHCAHTOA for sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. SOHCAHTOA. It's important to note that this is all only right now for right triangles. We'll learn later on how to adapt to a non-right triangle, but for now we can really only use this with right triangles. So one of the things we're going to talk about is solving a right triangle. And when I talk about solving a right triangle, I want to talk about solving the whole thing. So I need to find all three sides, all three angles. You're usually given some combination of sides and angles. And those combinations of sides and angles are typically sufficient to solve the whole triangle. Otherwise, you wouldn't be able to solve it. Well, we can probably figure out how to solve the sides. You might be wondering how we go about solving these angles. So there's one more thing I need to introduce before we try a couple of these problems, and that's to say that in order to find an angle theta, we use what we call inverse trig functions. Inverse trig functions. So just as we have any other function that undoes another function, right? Square and square root, f and f inverse. We have inverse trig functions too. So for example, the example that I've kind of tended to use is if sine theta is, say, 5 over 7, right? I've got a triangle here whose opposite side is 5 and hypotenuse is 7. Then I can solve for theta by undoing sine, and we have two notations for this. One is arc sine, which our book uses more often. But everywhere else I tend to see sine inverse much more. And this is the notation that you see on our calculator. And we have these for all the trig functions, right? So if I have sine, I have sine inverse, and I have arc sine. I have inverse cosine, and I have arc cosine. I have inverse tangent, and I have arc tangent. Our book tends to rely heavily on arc sine, arc cosine, arc tangent. I like to use inverse, whichever one you prefer, but the biggest thing to note, there you go, is that sine inverse of theta, writing it this way, is not the same as 1 over sine theta. There's a specific function that we know that we have that represents 1 over sine theta, the reciprocal function, that we'll talk about later on. So if I want to find an angle theta, given sides, we use inverse trig functions. One small other helpful hint, of course, is remember that there are 180 degrees in a triangle. So let's try some examples. So here's my first triangle to solve. I have an angle, or technically two angles, right? Because we know that this is a right triangle, and a side length. So I want to find all three sides, right? So that would be the segments PQ, QR, and PR. And I want to find all the angles. So that'd be angle P, angle Q, and angle R. Okay. Well, we know a few pieces of this already. We know that PQ is 7 centimeters. We know that angle Q is 90 degrees because it's a right triangle. We know that angle R is 72 degrees. I just need to find the other three pieces. Well, let's start with the easiest one to find. The easiest thing to start with is to find P. Because I'm given two angles, and I know that there are 180 degrees in a triangle, right? So I know that P plus Q plus R equals 180. Well, Q and R equal 162, right? 90 plus 72. So I subtract and I get 18. Yeah, 18 degrees. Great, so I've got three angles. I like to label them as I get them in my triangle, but that's personal preference. Okay, so this is where we're going to use the trig functions. I'm given, let's just say relative to 72, I guess. I'm given relative to 72 the opposite side. So which trig function uses the opposite side? Sine uses the opposite side, and tangent uses the opposite side. Right, my options are sine. Right, I know that sine of 72 is going to be opposite 7 over the hypotenuse, which is PR. Or I know that tangent of 72 is going to be the opposite side, which is 7 over the adjacent, which is QR. I can use whichever one I want. I prefer just to stick with sine. That's just me. So I'm going to go ahead and solve this. One of the things you want to really be careful with when you solve this is to make sure that your calculator is in degrees, right? I'm given degrees. So make sure your calculator, remember IB calls it your GDC, make sure your GDC is in degree mode. So we're just going to rearrange some things. So I know that based on my relation here, PR is 7 over sine 72, which is going to be approximately, oops, make sure I'm in degree mode too. Yep, we're good. So approximately 7.36, and then our label, of course, is centimeters. So we get PR. 7.36 centimeters. One more side to solve. And I can either use my tangent, right? I could also, if I wanted to, use the Pythagorean theorem. Sometimes that's not as accurate because you're rounding, so I actually do prefer to stick with the trig functions. So you could stick with tangent, right? Tangent of 72 is going to be 7 over QR. Or I could use, well, now I know hypotenuse, so I could use cosine, right, to find my adjacent side over 7. Again, I prefer to stick with what's given, so I like to use tangent here, but you could use cosine if you wanted to. So I'm going to stick with tangent. So rearranging again, QR is 7 over tangent 72. Okay, so 7 over tan 72 gives me approximately 2.27 centimeters. So now you can see, right, I have all three sides and all three angles, so my triangle is solved. I'm going to work through one more. If you're comfortable with this, you can skip ahead, but I just want to demonstrate it just to kind of hammer it home. Remember that I've got three sides and three angles, and I know two sides, right? I know 11, and I know 15, and I know, of course, that this is a right triangle, so y is 90 degrees. We're better off trying to find the angles first. So let's do this, well, it doesn't really matter which one I pick, so let's just pick angle x. So I've got the side opposite x, right? This is the opposite to theta. And this is the side adjacent to theta. So knowing opposite and adjacent, SOHCAHTOA, this is tangent, so I know that tangent of theta is 11 over 15. And I said to solve for theta, I can use my inverse trig functions. So if tangent theta is 11 over 15, theta is inverse tangent of 11 over 15. So just a quick calculator press, right? Calculator operation, and I get 36.3 approximately degrees. This is x, right? This is tangent x, so I should be consistent here. Tangent x. X is 36.3. And we know that there are 180 degrees in a triangle, right? So I know that x plus y plus z equals 180. So 126.3 plus z equals 180. So just by subtracting, I'm going to get z equals 53.7 degrees. And again, I've got some options. All I've got left here is my hypotenuse. I could use the Pythagorean theorem if I wanted to. I could also use a trig function. Here, actually, I think I'm just going to use the Pythagorean theorem because I didn't have to round to get any of my sides. It was given to me. So z squared equals x squared plus y squared. This is going to be 121 plus, I believe it's 225. So I solve this, oops, and I get approximately 18.6 units centimeters. So once again, you can see all three sides, all three angles, everything is labeled. I'm done. I'm good to go. The way this is going to get a little more complicated, IB likes to put these into three-dimensional space. IB loves to put things in what they call cuboids, which is just a word for prism. A rectangular prism specifically. I personally am not a spatial person. I like to mark this up as much as I can, draw cross sections, draw isolating information. So I'm going to kind of walk through my thought process here, but IB loves to do stuff like this. So much that this is an applications topic too. So find the angle between the diagonal CE and the plane ABCD. Give your answer to the nearest degree. So we're talking about, let's see, the diagonal CE. So that's from here to here. So this blue line to the plane. If we're talking about to the plane, I need some angle, some line here that kind of represents it. But if I think about this diagonal coming off of, see if I can color it in here, coming off of this plane here, right, ABCD. Right, if I were to imagine it kind of rising, then the angle it would make would be with the diagonal that shows up in the plane as well. So I want to find, actually I'm going to put this in a darker color. I want to find this angle, still not enough. Oh, a completely different color. Yeah, I want to find that angle. So I have a lot of unknowns here. There's a lot that I do know though, because this is some kind of a rectangular prism, every single intersection here between edges is perpendicular. So I have some kind of a right triangle situation everywhere. What I like to do is to isolate my given information and the things I want to focus on. So the triangle we've really formed here that seems important is this triangle here, ACE. And it's a right triangle. And because it has height 2 centimeters, I know that AE is 2 centimeters. And I want to find this angle right here. All I need to do is find one other side and I can figure this out, right? And I'm looking at my given information. What's the most obvious thing? What's the easiest thing I can solve for? Well, if I look at AC, right, this also forms the hypotenuse of another triangle. AC forms the hypotenuse of triangle ABC. Here, AB is 4 and BC is 3. So keep in mind that this here and this are the same length. They're the same side. I have enough information from ABC to solve for AC. I know from my Pythagorean theorem, and you probably know by now that 3, 4, 5 is one of the Pythagorean triplets. AC is 5 centimeters. So now I've got enough information to solve for my angle in question, right? Because I have two sides, and any trigonometric function that I can use is the ratio between two sides. So what do I have here? Well, relative to theta, I have the opposite side and I have the adjacent side. So out of SOHCAHTOA, this tells us that tangent is the function that I want to use, and I know that tangent of this angle is 2 over 5. So I can use my inverse trig function to solve it. This inverse trig function always produces an angle measure, and I get 21.8 degrees, but my problem asks for the nearest degree, so let's make sure I round. 22 degrees. So visualizing in 3 dimensions can be really tricky. So one thing that I find helpful, extremely helpful, is to isolate kind of important 2-dimensional figures that I can make as I'm working these problems out in 3 dimensions. So kind of focusing on a smaller piece before I go back and out and look at the big picture.